Lewis electron dot structures of molecules. Last time we did atoms and ions. Today, molecules. Now, the big goal of all this is really to get these structures, to get these molecular shapes of different molecules. We're not going to get there today. We're just going to master writing Lewis electron dot structures. Now, one of the really nice things that these shapes are going to allow us to do is to predict whether a molecule is polar or not. In other words, the electrons hang out more often on one end than the other ends. So that makes one end more negative, other ends more positive. So there's not this equal sharing of electrons, okay? And when that happens, we're going to call those molecules polar, and that really affects their chemistry and their physical properties. So right off the bat, here's a question for you. Is this a visualization of covalent or ionic bonding? It's definitely covalent, because ionic is a crystal, right? We have a crystalline structure. Cations surrounded by anions. No, not the case here. We have individual molecules flying around in the air, okay, if it's a gas, interacting if they're a liquid. Covalent bonding. What is covalent bonding? Well, covalent bonding is what holds all molecules together. So, for example, let's say you have a molecule, carbon monoxide, and you have a carbon atom and an oxygen atom. Maybe a good way to picture this is that you have this cloud of electrons between the two. The carbon nucleus is positive, the oxygen nucleus is positive. So both of these nuclei are attracted to that center cloud of electrons. And we can use fancier words than clouds. We can talk about orbitals and those sorts of things. But that's the general idea behind a covalent bond, is that these electrons are shared throughout the molecule. Nobody really knows whose electrons are whose. But what keeps the whole thing together is these positive nuclei are attracted to those clouds of electrons between the two atoms. What types of atoms form covalent bonds? If we take a look at the periodic table, pretty much the entire periodic table here is metals. Well, metals don't form covalent bonds, only nonmetals. So this section right here, that's where we see our molecules forming, only between nonmetals. So if you ever see a metal, you know it has to be an ionic compound. Covalent bond formation reaction. We've got a hydrogen atom. There's its Lewis dot structure. There's a Lewis dot structure for another hydrogen atom. And then we have a hydrogen molecule, H2. And we're not going to be drawing the dots for the bond. We're just going to be drawing this individual line for covalent bond. What is the octet rule? The idea behind the octet rule is that, take a look at these noble gases. They are really stable. They don't react with anything. The reason why they're so stable is because they are surrounded by 8 electrons. See? Each of these is surrounded by 8 electrons. Well, not helium, obviously, but neon through radon all have 8 electrons around them. That's the octet rule. That's why fluoride is so stable, because you give it 1 more electron and it will have 8 valence. Give oxygen 2 more electrons, it'll have 8 valence. Give arsenic 3 more electrons, it'll have 8 valence. So that's why those ions formed. But the idea behind the octet rule is, hey, have 8 electrons around that atom and you're going to be stable. So the question is, does the above hydrogen molecule obey the octet rule? Well, definitely not. Each hydrogen is only surrounded by 2 electrons. So, nope. What is the difference between single, double, and triple bonds? Well, that's kind of obvious, right? You have a double bond or you have a triple bond. Okay. Only atoms of these elements form double and triple bonds. This is a useful rule to remember. CNOS, carbon, nitrogen, oxygen, and sulfur. You're only going to see multiple bonds between these elements. So when we're drawing Lewis dot structures, if you do not see these elements, do not draw multiple bonds between them. And we'll be practicing that pretty soon. So what does it mean if a covalent bond is polar? Let's go back to our carbon monoxide molecule. In between the 2 atoms, we had this cloud of electrons. And we talked about sharing. of those electrons. I don't like the idea of sharing. I kind of prefer the term tug of war, because that's really what's going on. The carbon nucleus is positive, oxygen nucleus is positive, and they're tugging on those electrons between them. One of them is stronger than the other one. Which element is the best at the tug of war? Remember? Fluorine. Fluorine is the most electronegative. It has the strongest tendency to tug on those electrons. So fluorine is numero uno. So our trend of increasing electronegativity is like that in the periodic table. So when we take a look at this molecule, carbon monoxide, the electrons are going to hang out more often around the more electronegative atom. And that definitely is going to be oxygen, because it's closer to fluorine. So we can write partial negative on that side, partial positive on carbon. And this is a delta symbol. It's partial. It's not a full negative charge. It's not a full positive charge. So this idea behind polarity, you can get some nice pictures. If you have both atoms are the same, well, it's equal tug of war, equal sharing. It's nonpolar. There's no polarity, right? There's no partial negative. There's no partial positive. It's the same charge everywhere. However, if one element is different, especially if you have something like fluorine, there's a very large electronegativity difference, you get a huge partial negative charge and a huge partial positive charge. Or you can get some nice pictures like these, where you have the red region indicates where the electrons are hanging out much more often. So we have our fluorine over here and our hydrogen over here. So partial negative, partial positive. Circle the bond below that is least polar. In other words, which bond has the least electronegativity difference? You see it? It's definitely that one, because they're the same. That's completely nonpolar. Indicate the partial charges for the bonds given below using those symbols, partial plus, partial minus. The element that is the most electronegative, make sure you give it the partial negative. Fluorine is the most electronegative, so it should be like that. Chlorine is closer to fluorine than hydrogen. And here, it's nonpolar. There isn't any polarity, so don't draw any partial charges. Here are some rules for writing the Lewis electron dot structures for molecules. Okay, let's just run through a general idea here and get some hints. Let's say here's our molecule, AB4. We want to write the Lewis electron dot structure for that molecule. Hint number one is the central atom is always first. So there's our central atom. He's central. Then the next thing in general that you're going to do is you're going to place all the other atoms around that central atom. So if A's in the center, and this is surrounded by, in this case, 4 B's. And then they want you to determine the total number of valence electrons present. So pretty much you just look up A and B in the periodic table and add up the Roman numerals. Add up the total number of valence electrons that you have to work with. Then in general, what you're going to do after you count up the total is you just make bonds with everything and then make octets around all the surrounding atoms. And anything left over, we'll put on the center atom. And if you don't have anything left over to put on the center atom, you might need to make double bonds or triple bonds. Do that only with these elements, CNOS. So I know that's kind of quick. Let's just try some of these and see if we can get them to work. Write the Lewis formulas for the following molecules or ions. Okay, we're going to start out with smaller things and work our way up. We have Br2. So we know it has to look like this. Let's count up our valence. We have 2 bromines. Each one has 7. So 2 times 7, we have 14 valence electrons. So we'll connect them, make octets. Okay, how many electrons did I use up? Let's count them up. I've got 2, 4, 6, 8, 10, 12, 14. I used them all up. I'm done. So my Lewis electron dot structure is right here. H2S. Now remember, hydrogen can only have one bond, so he's not the center. S has to be the center. Let's count up the number of valence electrons. We'll have 2 times 1 for the hydrogens, plus only 1 sulfur atom, so add on 6 more. That's 8. So the first thing we do is connect. Hydrogen is done with 1 bond. So anything left over, put on the center atom. We've used up 2, 4, 6, 8. So we have 2 lone pairs of electrons, it's called. To make sure we've used them all up, 2, 4, 6, 8, all electrons are used up. That's good. IBr2 plus. Iodine is first, so it needs to be in the center. And whether you draw these linear or bent, it really doesn't matter right now. We're just drawing them out. Let's find our valence total. We have 2 bromines. They have 7 electrons. We have iodine. That has 7 electrons. So we really have 3 times 7 is 21, but it's a plus charge. So subtract 1. So we really have 20 valence electrons. And I subtracted 1 because I have a positive charge. If I ever had a negative charge, I have to add electrons. So let's first connect them. Make octets on all the surrounding atoms. Anything left over, put on the center atom. 2, 4, 6, 8. 2, 4, 6, 8. Okay, how many have I used up? 8 with each bromine. That's 16. I have 4 left. I've used them all up. Everything has an octet. I just need to make my brackets with my positive charge. HNO2, and here's our structure, HONO. Okay, let's count up our valence. 1 for hydrogen. Nitrogen has 5. Each oxygen has 6. 18 total. So hydrogen has 1. Let's just make octets on everything. Nitrogen is our center atom. So let's see how many we've used up, and if I have anything left over, I put it on that center atom. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So there's 18. Now does everything have an octet? And remember, hydrogen is happy with 1 bond. So my hydrogen looks good. My oxygen has 8. This oxygen has 8. This nitrogen is short on electrons. And we can't just add 2 more electrons because we only have 18 electrons to work with. So remember, CNOS, double and triple bonds. This will work. We have nitrogen and oxygen. So let's take these 2 and put them right there. What would it look like? We'd have H, O, double bond, N, O. That works. Now everything has an octet. Do you realize we could have, let's take this pair and move them in instead. Then we would have had H, O, so we have our lone pairs looking like that. Double bond. Everything still has an octet. We have 2 possible answers here. One of them is better than the other one. We'll learn more about that next class period. Cyanide, carbon and a nitrogen. Carbon has 4 valence electrons, nitrogen has 5. So 4 plus 5 plus 1 for the charge. That's 10 valence electrons total. So make a bond. It's 2, 4, 6, 8, 10. I better stop. Nitrogen's not even close to an octet. However, remember CNOS. So I can make double bonds. So let's try moving this lone pair in here. But then nitrogen would only have 6. We have to do it again. If you move 2 lone pairs in there, what would that look like? We'd have carbon, nitrogen. Still have this lone pair. We still have this lone pair. Now we have triple bond. Does everything have an octet? 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for nitrogen. How about the entire total? Do we lose our 10? 2, 4, 6, 8, 10. It works. Don't forget the brackets for the charge, and you'll have it. Okay, carbon has to be in the center, surrounded by an oxygen and 2 bromines. Let's find our valence total. 4 for carbon, 6 for oxygen, 2 times 7 for bromine. So I have 24 valence electrons total. So let's connect everything, and let's make octets and see if we can get lucky here. Okay, I used up 8 around each surrounding atom, so that's 24 electrons, so that's good. But does everything have an octet? No, carbon doesn't, but remember CNOS. So let's make a double bond between carbon and oxygen. Move that in there. So we would end up with carbon, bromine has its octet, oxygen, and now we have a double bond there, and this bromine has its octet. So here's our answer. All right, let's try this compound. ClF2+. So we have a chlorine and 2 fluorines. So for the number of valence, 3 times 7 minus 1, about 20 valence electron. So let's make our covalent bonds, make octets on all the surrounding atoms, and anything left over we put on the center atom. So I've used 16, 18, 20. I need brackets for a positive charge. I'm done. Let's try diphosphorus. Each phosphorus has 5 valence electrons. So 2 times 5 is 10 valence electrons. Two, 4, 6, 8, 10, 12, 14. Way too many. 2, 4, 6, 8, 10. There's 10. All right, now the hint here is that P obeys the octet rule, so we have to keep going. We have to make double bonds even though we're not obeying CNOS. So let's move these in there and see if we can get it to work better. So each phosphorus obeys the octet rule, and we have 2, 4, 6, 8, and we have 10 valence electrons. There's our answer. We couldn't have answered it without that hint. NF3. Nitrogen has to be in the center, surrounded by 3 fluorines. Nitrogen has 5 valence electrons. Each fluorine has 7. So that's 26 valence electrons total. So first connect everything, make octets on all the surrounding atoms. Anything left over, we'll put on the center. Okay, I've used 24 electrons so far, so I have 2 left over. Goes on the nitrogen atom. Nitrogen has an octet, everything has an octet. There's our answer. We're done. So in general, when writing these Lewis electron dot structures, there's several general strategies. One is the first atom is always in the center. The next thing you do is surround that center atom with all the surrounding atoms. Then you count up your valence electrons and make octets on all those surrounding atoms, and anything left over you put on the center atom. And remember CNOS. That's the only time you can make double and triple bonds to try to arrive at that octet for all atoms in your structure.